Artificial intelligence is evolving at an unprecedented rate,
Transformer
and the
squared
latest
model.
advancements are
Then, later in
downright
this video,
mind-blowing.
we'll uncover how DeepSeek
Imagine an AI that can reprogram itself in real time to handle brand new tasks. No retraining, no extra data, just instant adaptation. This is a monumental leap, all thanks to Sakana AI's groundbreaking Transformer squared model. But that's not the only breakthrough we'll explore. Later in this article, we'll uncover how DeepSeek's latest open-source model is rivaling OpenAI's flagship AI, not with billions of dollars in funding, but with a budget closer to the price of a mid-range smartphone. Adaptation is one of the most remarkable phenomena in nature. From the way an octopus can change their skin color to blend into its surroundings, to how the human brain rewires itself after an injury, allowing individuals to recover lost functions and adapt to new ways of thinking or moving. Living organisms exhibit adaptability that allows life to flourish in diverse and ever-changing environments. In the field of AI, the concept of adaptation holds a similar allure. Imagine a machine learning system that could adjust its own weights dynamically to thrive in unfamiliar settings, essentially illustrating a system that evolves as it learns. Self-adaptiveness in AI promises greater efficiency and the potential for lifelong models ever aligned with the dynamic nature of the real world. Transformer Squared, where we propose a machine learning system that dynamically adjusts its weights for various tasks. The name Transformer Squared reflects its two-step process. First, the model analyzes the incoming task to understand its requirements, and then it applies task-specific adaptations to generate optimal results. By selectively adjusting critical components of the model weights, our framework allows LLMs to dynamically adapt to new tasks in real time. Transformer Squared demonstrates significant advancements across various tasks, for example, math, coding, reasoning, and visual understanding, outperforming traditional static approaches like LoRa in efficiency and task-specific performance while requiring far fewer parameters. Our research offers a glimpse into a future where AI models are no longer static. These systems will scale their compute dynamically at test time to adapt to the complexity of tasks they encounter, embodying living intelligence capable of continuous change and lifelong learning. We believe self-adaptivity will not only transform AI research, but also redefine how we interact with intelligent systems, creating a world where adaptability and intelligence go hand in hand. Buckle up, because this is the kind of innovation that's rewriting the AI rulebook. Sakana AI's Transformer Squared Self-Adapting AI. Sakana AI, an AI research lab known for nature-inspired algorithms and ultra-flexible systems, recently introduced Transformer Squared, a language model capable of learning new tasks without the usual time-consuming fine-tuning process. Izrania, a language model capable of learning new tasks without the usual time-consuming fine-tuning process. Typically, adapting a large language model, LLM, for a new task requires specialized techniques like LoRa, low-rank adaptation, which tweaks only a subset of the model's parameters, saving time and resources compared to retraining the entire model. But Sakana AI's approach goes a step further. Their model dynamically reconfigures its own weights during inference, meaning it fine-tunes itself on the fly, rather than requiring separate training sessions. Just as the human brain stores knowledge and processes information through interconnected neural pathways, LLMs store knowledge within their weight matrices. These matrices are the brain of an LLM, holding the essence of what it has learned from its training data. Understanding this brain and ensuring that it can adapt effectively to new tasks requires a closer look at its inner structure. This is where singular value decomposition, SVD, provides invaluable insights. Think of SVD as a surgeon performing a detailed operation on the brain of an LLM. This surgeon breaks down the vast, complex knowledge stored in the LLM into smaller, meaningful, and independent pieces, e.g., the different pathways or components for math, language understanding, etc. SVD achieves this purpose by identifying the principal components of the LLM's weight matrices. In our research, we found that enhancing the signal from a subset of these components while suppressing the others could improve an LLM's performance on downstream tasks. By building on this foundation, Transformers Squared takes the next step toward dynamic, task-specific adaptation, enabling LLMs to excel in diverse and complex scenarios.
Then, later in this
Transformers
video,
Squared
we'll
is a
uncover
novel approach, pioneering the concept of self-adaptive LLMs, with a two-step process that redefines how these powerful models tackle diverse tasks. At its core is the ability to dynamically adjust critical components of its weight matrices. At training time, we introduce singular value fine-tuning, SVF, a method that employs reinforcement learning, RL, to enhance, suppress the signals from different brain components for various types of downstream tasks. At inference time, we employ three distinct strategies to detect the identity of the task and adapt the model's weights accordingly. The figure below gives an overview of our Methotransformer Squared utilizes singular value decomposition, SVD, a linear algebra technique to break down the model's weight matrix into smaller components representing different skills like math, coding, or language understanding. During training, Sakana's researchers extract specialized Z-vectors from these SVD components, which act as adjustable skill dials. At inference time, we devise a two-pass adaptation strategy for our framework that effectively combines the set of task-specific Z-vectors. In the first inference pass, given a task or an individual input prompt, Transformer Squared analyzes its test time conditions using one of the three adaptation methods below. In the second pass, Transformer Squared then modulates the weights accordingly by combining the Z-vectors, producing a final response most relevant for its new settings. We summarize the three methods for task detection / adaptation in the following. 1. Prompt-based adaptation. A specifically designed adaptation prompt classifies the task, e.g., math, coding, and selects a pre-trained Z-vector. Second, classifier-based adaptation. A task classifier trained with SVF identifies the task during inference and selects the appropriate Z-vector. Third, few-shot adaptation. Combines multiple pre-trained Z-vectors through weighted interpolation. A simple optimization algorithm tunes these weights based on performance on a few-shot evaluation set. These three methods collectively ensure that Transformer Squared achieves robust and efficient task adaptation, paving the way for remarkable performance across diverse scenarios. When a user inputs a prompt, the model, 1. Identifies relevant skills needed for the task. Second, selects and applies the appropriate Z-vectors to the base model. Third, instantly optimizes itself for the task without requiring extensive fine-tuning. This process, called Singular Value Fine-Tuning, SVF, allows Transformer Squared to outperform traditional fine-tuning methods. Sakana AI tested Transformer Squared on models like Llama 3 and Mistral, comparing performance to traditional LoRa fine-tuning. The results? Better performance across various tasks like math, coding, reasoning, and visual question answering. Even more impressive, Z-vectors can be transferred between models with similar architectures. For example, Z-vectors trained on Llama 3 may be reusable on Mistral, though they perform best when fine-tuned for each target model. The best part? Sakana AI has open-sourced its code on GitHub, allowing developers to experiment with this cutting-edge technology. DeepSeek-R. 1. The open-source AI that's rivaling OpenAI for a fraction of the cost. Just as the AI world was digesting Sakana AI's breakthrough, another major development emerged. Chinese AI startup DeepSeek unveiled DeepSeek-R1, an open-source model that challenges OpenAI's GPT-4o, but at a fraction of the cost. How DeepSeek-R1 achieves cutting-edge performance. DeepSeek-R1 is based on a mixture of experts model called DeepSeek V3. What makes it special is its focus on advanced inference time customization, allowing it to dynamically improve reasoning and complex problem-solving skills. DeepSeek-R1 achieves performance on par with OpenAI's GPT-4o, but at 90 to 95% lower costs. For example, OpenAI's GPT-4 pricing, $15 per million input tokens, $60 per million
squared
output
model.
tokens.
Then, later in this video,
DeepSeek
we'll
R1
uncover
pricing,
how deep...
$0.55 per million input tokens, $2.19 per million output tokens. For startups and enterprises handling high query volumes, this cost reduction is a game changer, making cutting-edge AI far more accessible. Performance benchmarks. DeepSeek R1 has matched or outperformed OpenAI's latest models across several key benchmarks. 79.8% on AMI, 2024 math tests. 97.3% on Math 500, beating GPT-4.0's 96.4%, 0.07%. 2029 rating on Codeforces, better than 96.3% of human programmers. 90.8% accuracy on MMU, compared to GPT-4.0's 91.8%. How DeepSeek R1 was built. DeepSeek R1 evolved from DeepSeek R10, an AI trained purely through reinforcement learning, RL. No supervised data. This zero-stage system learned reasoning skills through trial and error across thousands of RL steps, significantly boosting problem-solving capabilities. However, early versions struggled with language fluency, sometimes mixing languages or producing hard-to-read text. To fix this, the DeepSeek team introduced a multi-stage approach blending supervised fine-tuning, SFT, with reinforcement learning, RL. This preserved the model's advanced reasoning while ensuring natural and readable text generation. Open-source accessibility. DeepSeek R1 is fully open-source under the MIT license, meaning anyone can use it for free. The model is available on Hugging Face, and developers can integrate it via API or run it locally. DeepSeek also introduced DeepThink, an AI assistant similar to ChatGPT. The future of AI? Instant adaptation and open innovation. Both Transformer Squared and DeepSeek R1 represent a shift toward AI models that adapt instantly, eliminating costly retraining. Here's how they compare. Transformer Squared fine-tunes weight components in real time, making it ultra-flexible for on-the-fly learning. DeepSeek R1 uses reinforcement learning and knowledge distillation to enhance reasoning and problem-solving at a fraction of traditional AI costs. With Google's Gemini, OpenAI's GPT-4.0, and other adaptive AI projects also pushing the boundaries, we're heading into an era where AI models will learn as they interact, just like humans. The open-source revolution. Both Sakana AI's Transformer Squared and DeepSeek R1 are open source, meaning developers worldwide can experiment, improve, and build upon these innovations. This democratization of AI will likely accelerate breakthroughs faster than ever before. If you're a developer, now is the perfect time to dive in. Sakana AI's code is on GitHub, and DeepSeek R1 is available on Hugging Face.